do this. Thank you very much for the kind introduction, Kai. Let me start by thanking the organizers, Heikung and Peter, for organizing this beautiful workshop and for the invitation. It's been fantastic. We're reaching the end, and I think we had fantastic tutorials and contributions, and showing how blossoming and broad this rather new field of research is. And so in my presentation, I will talk about Magnonic interconnected nanowire arrays, such as this buckyball structure, which was so nicely introduced in the tutorial that Laura gave this morning, and with a focus on the Magnonic properties of these systems, how high-frequency magnetic oscillations develop in such systems, and with a perspective on how to perform micromagnetic simulations on this. So after, again, this fantastic tutorial, there's hardly anything I need to tell about the transition from 2D spin-ice system to 3D spin-ice systems. I'm adding this transparency for the sake of completeness. As we know, spin-ice systems are very fascinating due to their numerous properties and potential applications, and the transition to 3D systems can open entirely new avenues. And we haven't worked very much on spin-ice systems in our research, but as these three-dimensional structures started to occur a couple of years ago, here's an example from the group of Michael Huth, that triggered our curiosity, and we said, yeah, well, it should be possible to simulate the magnetic configuration and the properties of these systems. So let's have a look at that. We were, of course, aware of this beautiful buckyball structure that Claire Donnelly had already prepared with Laura several years ago. But it was kind of a singular, object at that time. And with the appearance of this modern fabrication techniques that Amalio has been talking about, this field is now gaining some traction. And so, I clicked on the wrong button. So the topic that we're addressing is somewhere at the intersection of three major topics in magnetism, I would say. The connection between 3D nanomagnetism and artificial spin-ice is what I already mentioned, and the tutorial by Andri has explained how magnonics in 3 dimension is of importance. And we were also motivated by a former study that we did with Sebastian Gliga, where the high-frequency properties or the magnonic properties of spin-ice systems were studied. And so we can combine these three and be somewhere at the intersection. And it's an interesting place to be because we get some input from different communities in there. And so this was essentially, what I will present is essentially the work of Rajesh Chinnikundil, his PhD thesis a couple of years ago, who studied, among other things, these diamond-type lattices, which I will discuss later, quite similar to what the group of Sam Leduc had been doing around the same time. So coming back to the very first presentation of this workshop by Amalio, who had addressed the importance of obviously three-dimensional magnetic nanostructures, but was focused more on the synthesis and the fabrication. Here I would like to point out that simulating such structures is a challenge from a simulation point of view, because we're dealing with, albeit being in the nanomagnetism regime, usually relatively large structures. We're dealing with complex geometries, often with smooth and curved surfaces. And in many cases, like in the arrays that I will be discussing, we have a small volume occupancy, which is an issue if you have a micromagnetic tool that requires a computational volume area that is cubic, basically, where you put your sample into that, and then if 99-something% of that volume is essentially air, you're wasting a lot of computation time and resources because you're only interested usually in the magnetic part of that volume. So if you're dealing with arrays of interacting particles, sometimes separate particles, that's also something that can be problematic. So theoretical studies on this topic require versatile and fast simulations, and we believe we are in a comfortable position in that sense with our code, which I wish to advertise here, and I wish to encourage you to have a look at it, to download it. It's an open source code. It's the code that I've been using and developing over several years, and that very recently I put out as open source code. It features a couple of interesting properties that can be useful for, say, common micromagnetic simulation tasks, like calculating the static structures, magnetic switching processes, the field-driven dynamics, the current-driven dynamics, hysteresis loops, and so on. From a technical point of view, it's quite optimized. It's written object-oriented C++. It features GPU acceleration and implements a couple of advanced mathematical techniques, which I don't have time to delve into. So again, I'm pushing all the wrong buttons. Just to show you how it basically works, it's rather simple. You first define the geometry. That's very simple to what, very similar to what experimentalists do when they have to define their three-dimensional sample. And then we move on to generating a finite element mesh. There are libraries and codes for that. Then we just have to provide the simulation parameters and describe which material we're dealing with and define the initial magnetic configuration. And then comes the major loop where we calculate the effective fields that enter the Landau-Lifshitz equation, and we integrate the Landau-Lifshitz equation. While doing so, we monitor the energy of the system and a couple of other parameters. And when the simulation is finished, we write the output. That's pretty standard. But if you keep in mind that the LLG integration time steps are usually in the sub-picosecond regime, and we often want to integrate over about, say, 10 nanoseconds, and we have typically 100,000 degrees of freedom, sometimes more. You have to calculate these effective fields over and over again. So it is good to have efficient numerical tools for doing this, and the GPU acceleration is quite helpful in that sense. And for the visualization, we can rely on ParaView, which, without being mentioned, has been used by many other colleagues in previous talks. So it's kind of a standard visualization tool for such complex geometries. Just to give you, I'll get back to the buckyballs very soon. I just want to show you how this looks in practice. You define a geometry, in this case, say a hemispherical shell, which you can do quite easily with CAD codes like the open source FreeCAD software. Then the input data is provided through simple ASCII files, and then you can run the simulation, which outputs some intermediate data to check that everything's okay. And in the end, you can visualize the magnetic structures and analyze the evolution in time of these processes. So if you're interested, please have a look at this and contact me if you have any problems or questions. I'll be happy to address these. Now, back to the physics of these structures. So why is the buckyball interesting? Well, it is, of course, an iconic shape, which is just beautiful. So one wants to calculate, as a simulation person like me, wants to know what the magnetic structure in these structures look like. But it's also a first kind of a generalization of a 2D artificial spin ice system to a three-dimensional one. In a sense, it can be considered as a wrapped up hexagonal lattice. Not exactly, because there are some pentagons in there, but in principle, it's the same thing as far as the vertex sides is concerned, with the difference that now they are on a spherical surface. And so this is a kind of a gentle transition from 2D to 3D. It's not yet fully three-dimensional, but it's a two-dimensional spin ice on a three-dimensional object. And so this can have what we wanted to investigate, where are there any differences between such three-dimensional geometries and the rather well-known two-dimensional ones? What is the static magnetic structure, things like magnetic frustration and the high-frequency excitations developing in these geometries, and whether there's a size dependence. And so here you can already see that the ability to discretize this sample with finite elements is quite useful, because with a relatively small amount of cells, we can have a very smooth geometric approximation. And we use the phi-bit material parameters to study this, and then we relax the structure at zero field. And what we get are then vertex configurations that can have different types of charges. Like here you see in the branches, the magnetization can point towards one point from all the three adjacent branches, or you can have some other configurations. Typically, the sizes we're looking at are bars of about 100 nanometers in length, which makes sure that, and a rather thin of about 20 nanometers, making sure that these can be considered as Ising-like macroscopic dipoles. And so therefore you develop some magnetic frustration at the vertices rather than domain walls within the wires. And so you can easily classify the two types basically of vertex configuration that can develop. The ice rule obeying state, which is 2 in, 1 out, or vice versa, which due to time inversion symmetry is equivalent, and what we call the defect states, where you have 3 branches where the magnetization is flowing towards the vertex, or 3 in which it flows away from it, where you end up with a triple charge. And we call this the defect configurations, as I said. Now, one thing that is already quite different from the two-dimensional hexagonal lattice is that we can generate this triple charge defect state kind of automatically by coming from remnants. So this is similar to an onion state in a disk. You would have a configuration of the magnetization on the sphere or on the network that is placed on the sphere, which has a strong preferential or a remnant magnetization direction towards the formally applied field, and where you have 2 vertices on opposite sides, one where the magnetization diverges and the other where it converges. So you can generate 2 of these defect structures just by saturating from remnants and saturating and removing the field coming from remnants. And interestingly, these defect charges are the first to disappear when you apply a negative field, which means that you can apply a minor loop and then return to 0 field and then obtain a defect-free structure. So we can classify the configurations at least 2 different ones, one which contains such defects and the other one which does not. And we have a kind of a recipe to switch from the one to the other. And so now we can look at how the high frequency oscillation of this structure behaves. We expose this sample to a short field pulse, and then thereby excite some ringing of the magnetization. And there are some pronounced peaks which are localized at the vertices, but that's not all. At higher frequencies, we have 3 rather distinct peaks, which, and this is strongly simplified, can be ascribed to a first, second, and third order oscillation within the wires. So these are modes that are localized within the wires. The boundary conditions are not exactly as described here. It's a little bit more complicated. But we get these first 3 modes here, and oscillation peaks that can be ascribed to the vertices. And that is for the case of the defect-free state. And if we have one that contains these 2 defects that I was talking about before, then they provide an additional, if you want, fingerprint in the Magnonic spectrum, a rather large absorption peak that develops at low frequencies when they're present. So by following the recipe that I said before of removing and inserting these defects, we can introduce or remove this peak and thereby kind of manipulate the Magnonic response of the system. Now I want to briefly discuss another method, numerical method that I developed with my friend and colleague Massimiliano D'Aquino, that concerns linearized dynamics of the magnetization, where we don't calculate the full LLG dynamics as is done in the TEDMAC code that I have described before, but only consider small variations of the magnetization around an equilibrium position. These are the situations that you encounter when you're dealing with Magnonic systems where the magnetization oscillates around an equilibrium. So you don't need to do a full, say, first principles calculation of the magnetic structure, but it's sufficient to account for small oscillations. And you can also assume that they are harmonic in time, and that they will lead to a variation of the effective field which has the same frequency. And by doing this linearization and plugging it into the Landau-Lifshitz-Gilbert equation, you can solve these kind of problems much more easily and much more rapidly than with the usual time domain simulations. So these are simulations in the frequency domain. You end up with equations like this, basically solving or getting the dynamic magnetization of the system boils down to solving a system of linear equations that you can then do for any frequency step rather quickly and thereby calculate the entire spectrum. And you also access the eigenmodes by this. Of course, I don't have time to go into all the details of this, but it is owing to these techniques that we were able to look a little bit further and see how the spectra that I had shown you with what's essentially the line here in the middle at the field H equals 0, how that evolves if we apply a positive or negative field and thereby calculate Magnonic spectra in acceptable time using this linear approximation. And for different configurations, one which is randomized and has no remnant magnetization, the spectrum looks symmetric like this, whereas in the case where we come from saturation and have a preferential direction, the magnetic field is applied either parallel or anti-parallel to this remnant magnetization, and then, until you reach a switching field, you get more or less linear slopes, so some kind of quite different response. And this is typically what experimentalists could measure. So moving on now to another geometry, having looked at this buckyball, we wanted to see how these true three-dimensional structures look like with, or how they behave in a micromagnetic sense. We came up with this connection of, or this set of interconnected nanowires, which we call the artificial Magnonic crystal, with the shape of a diamond lattice, since the vertex points are located at positions corresponding to those of a diamond. And here again, the finite element method allows us to approximate the shape very nicely and to limit the computational region to the magnetic region only. So this is still a rather small sample of just 500 nanometers in size, but it's large enough to study several features that we will investigate there. One of which are the static vertex configurations that we can find. We have the 2-in, 2-out neutral configuration, and another configuration which is charged, where we have 3 branches going out and only 1 going in, and the opposite one with the 3-1, 1-out charge. And perhaps interestingly, this ice rule obeying state is degenerate, contrary to what you have in square lattices with the same coordination, where you have type 1 and type 2 lattices. That is because the projection of 2D basically lifts a degeneracy which you have in 3D that is given by the fact that all the wires enclose the same angle. And so there is no distinction between bars that are head-to-head or next to each other as you have it in square lattices. There's only one type of these vertices, and these are the charged vertices that you can find there. And coming again from saturation down to remnants, we can generate different configurations if we apply the field in, say, a diagonal, if you want, a direction, intermediate direction, which does not correspond to any direction of the wires, and you lower it to 0 field, then all the vertices are defect-free, and you just have magnetic charges at the outermost branches of this crystal. Whereas if we apply the field along one direction that is given by these wires, we can have alternating stacks of positive and negative charges, an ordered charged configuration. And of course, if we start from a random configuration, we can have all sorts of different vertices and different types appearing in the lattice. And so, of course, we wanted to do the same study as I've shown you before, and see what happens in terms of the high frequency response. And we can identify peaks that can be correlated to geometric features of the sample. There is one which is a surface mode where only the free dangling ends oscillate at rather low frequencies. We have the vertex modes, which is the most prominent one, where all the vertices oscillate at a well-defined frequencies. And we get, again, nanowire modes like in the buckyball that roughly describe the first, second, and third order oscillation within the wires. Now that was for the ordered state. If we introduce defects, then things become a little bit more complicated. You get 2 different profiles here. At different frequencies, you have different vertex types oscillating. This is what you see here. These 2 peaks correspond to the 2 images that you see there, with the defect mode having a slightly lower frequency. So we don't have only geometric features that show up in the magnetic fingerprint, but also the micromagnetic configurations that reflect as peaks of the magnetization. So, and perhaps you have noticed that the peaks in the nanowires have kind of disappeared or broadened out. We attribute this to the fact that the defect charges represent sources of the magnetic field which perturb or modify the oscillation in the adjacent wires. Moreover, the micromagnetic boundary conditions are different. Whether you have a defect on one side or not, you have, say, a domain wall, basically, that is absent in the other case. So this means that there is a quite broad spectrum of different nearby frequencies rather than the 3 well-defined peaks which you get in the ordered state. And talking about defects, we also wanted to know what happens if we introduce an actual defect by removing physically one bar and introducing the geometric defect, as we call it, and thereby lowering the local coordination of the vertices. And that also shows up as a tiny peak. Well, it's tinier because there's only one such defect. If we had more, it would probably be larger. But anyway, it confirms again that any geometric feature and any micromagnetic feature has kind of its own fingerprint. And here you can see that frequency where only the vertices near to that structural defect are oscillating. This is kind of reminiscent to what you can find in real crystals in color centers when you have a defect. Then around there, the electromagnetic waves have different properties. We can simulate with the methods I mentioned before some rather, I think, beautiful magnospectra in this type of diamond lattice. Here we only looked at the defect-free state. It would be too complicated. This is kind of reminiscent to what Bill has shown this morning in the hybridization effects, but we're not sure it's really the same physics. These are still the distinct modes here. The line in the middle is the one that we have discussed so far. And as we apply a field either perpendicular to the saturation direction or along it, we get some different magnospectra. This again is similar to what the community has been doing in square spin-ice lattices and leads to comparable spectra. So not something where you would say, okay, the three-dimensional aspect has significantly changed something. Rather, it confirms what we already know from 2D. What we were looking for is, or what we thought we would have found, I must be prudent in the statement, is some kind of a macroscopic spin wave, where we thought it would be nice to generate something which could be a magnetic metamaterial where the dynamic properties are determined by the geometric features of this crystal, so that you can maybe host spin waves whose frequency and the wavelength is correlated in some sense with the geometric size of these bars and not to the magnetic material itself. And here we were encouraged by seeing that it seems to be a breathing or pulsating mode which starts in the middle and moves to the outer side after a single pulse being applied in the direction perpendicular to the plane there. And I thought, oh yeah, that's interesting. Let's try to see whether we can find such waves. And Ashfaq, my student here in the audience, has tried to simulate this, but I cannot show you results on this because the results were negative. I just want to show you that we have studied very long arrays of wires. We could simulate now really much larger structures than those that you have seen here before. Sorry. And still, we were unable to really detect a propagating macroscopic spin waves. We find the same features as in the smaller array where the vertices and the wires and the surfaces oscillate, but there is no macroscopic correlation that would be significant. This paper was already mentioned in the talk by Andre. It has appeared just a few days ago. It's a nice collaboration where Mateusz has done the lion's share of the work. We have been using mostly the numerical methods I have been talking about before. So this is a similar approach. You have a complex 3D geometry, the gyroid in this case, and we could combine this with experimental studies and confirm, at least qualitatively, the findings that we get there. We get an angular and field dependence of the peaks. You can see where these are localized. And Olivier has asked a question about the internal fields, and yes, it does play a role. I already talked with him about this, but we have verified this by looking not at a cube like this, but at an elongated rectangle, where what we call a macroscopic surface anisotropy plays a role, shifting the peaks to some directions which correspond to those that we find in the experiments, because in the experiments, the gyroids are essentially very extended, millimeter-sized thin films. Even though they are thick, they have a macroscopic aspect ratio, which is really huge and which we cannot consider in the simulations. So there is this microscopic feature that is responsible for the local ordering of the magnetization in the gyroid, and a macroscopic aspect that is due to the shape of the gyroid itself. We also looked, but this I will be brief on that, on a regular array of nanowires, and there we have a larger number of possible charges, except for the situation where all 6 point to the same direction. That does not seem to be stable. We didn't find any vertex that would sustain such a highly frustrated configuration. And we could see that basically we find the same behavior. The surface is oscillating at a specific frequency. The vertices inside the sample have their own frequency. The nanowires have distinct frequencies. And depending on the magnetic configuration, we get different peaks when we have these magnetic defect type structures that occur. So to summarize, I briefly talked about the method, which is our finite element code TETMAC, which again I invite you to have a look at. And we also used the linearized magnetization dynamics tools that were developed with Massimiliano to determine eigenmodes and the linear response in Magnonic systems. We looked at interconnected nanowire architectures for three-dimensional artificial spin ice, and looked at buckyball diamond type structures, regular arrays and gyroids, and found that the configurations at vertices has a distinct signature in the high frequency spectrum. To some extent, it is switchable as we can introduce or remove such defects. And the search for collective spin wave modes the spin wave mode, we found them in nanowires, but they're still basically k = 0 modes. The propagating spin waves have not yet been identified in the simulations, let's put it this way. Let me close by thanking the main collaborators, Massimiliano D'Aquino, who I mentioned already a couple of times, with whom I started a very productive and successful collaboration. Much of this work was done by my former PhD student, Riccardo Kundil, and Julien Bauer, an intern, has contributed a lot in the development of the linearized code. Finally, I want to thank the funding agencies and you for the attention.